So Kamran will tell us about the cosmological bootstrap.
Okay, great. Thanks for organizers for this great conference in this beautiful location. So today I'm going to talk about work titled Non-perturbative cosmological bootstrap in collaboration with Monte and João. So let me start with a very brief motivation that de Sitter physics is, de Sitter is the simplest model for expanding universe. It's a good approximation of the early time universe inflation, and even now. And there has been a lot of studies in this context, but you see there are some remaining questions, basic question about quantum field theory in fixed non-dynamical background of de Sitter. Some of them I mentioned here under umbrella of cosmological bootstrap, and also the dictionary between de Sitter and Euclidean ADS, which both of them are perturbative calculations. But our approach is mostly like the conformal bootstrap approach, where we want to study implication of general properties like symmetry, like Western symmetry, other symmetries, and also unitarity. So here I just give a quick review of what happens in conformal bootstrap. For example, you have a 4-point function, and you expand it in conformal blocks with some coefficient coming from OP coefficient, which are positive, at least for this all identical correlator. And we know this conformal blocks, and you can expand this 4-point function to different channels and put them equal, and then find some bounds on CFD data. And this led to the most precise determination of 3D isomodel. Bootstrappers are so proud of. So the ideology here is the same. So we will have some 4-point function that we talk about how to get there. Now as an integral instead of sum over principal series that I talk about, but some integral instead of the sum. And instead of conformal blocks, you have conformal partial waves, which are also known function and can be written in terms of conformal blocks actually. And with some coefficient i's that we call partial wave coefficients, they also have positivity conditions. Okay, that's the spoiler right there. Great. So let me just set the notations with reviewing quickly basics of de Sitter. So if you have a de Sitter d+1, it's actually defined as a hyperboloid in Minkowski space of d+2, like that. It's a maximally symmetric spacetime with constant positive curvature. And there are different type of slicing this spacetime, but the one that we are focusing on is flat slicing. And this particular coordinates, conformal coordinates, that you take this parabola and you cut it like this, and each slice for constant eta, which is conformal time, that runs from -infinity early times to 0 late time boundary, and each slice is some Rn Euclidean flat space. And you can see here, this is like the Penrose diagram, that each constant eta is one of these red curves, supposed to be red, but anyways, so the symmetric group of ds is SOD plus 1,1, which gave that the generators of the isometries will have the commutation relation of conformal algebra, which will be very important. So a bit of representation theory, which is or construction, the Hilbert space construction we have, will be infinite dimensional, labeled by quantum numbers, spin and scaling dimensions, and this is very well studied by mathematicians. So there is a lack of good intuition, physical intuition. Anyways, the principal series is one set of them that has complex dimensions, d/2 plus I nu, and it corresponds in free massive scalar to heavy fields. And there is another part, it's complementary series, which goes for light fields. And it's from d+2 plus some real number. Usually the C is from 0 to D for spin 0, and for higher spins it's a bit smaller. and some sort of discrete series, which are integer or half integer. And I don't go through the details, but they show up, at least in our examples, of scalar field in d equal to 1, not other than that. In this flat slicing, we have this state within each multiplet. We have this states that labeled by A, the spins, and also X in this constant slicing, constant eta slicing. And this state transform are like primary operators under this DS symmetries. Two of them I wrote here, P and dilatation, and the rest too. And one can use these states for a completeness relation, resolution of identity, which is sum over spin and an integral over this continuous delta, and the integral over the space, all of this x over Rn. So now I go to a brief introduction with like boundary operators. So you can take this bulk operators phi, and you take them to eta equal to 0, late time boundary, and you can expand them in the eta, small eta, and they're going to be these operators, okay, with dimension delta k, which are unrelated to the delta I showed. They can be generic complex dimension. And the action of DS isometry on these ones are again like conformal algebra action. And the hermiticity of the theory will give that these delta k's are in pairs of delta and delta star. Because O dagger will be delta star. An important fact is that there is no state operator correspondence, unlike ADS here. So now let's take a 2-point function of bulk operators and inject that resolution identity between these two operators. Then each part here is fixed by de Sitter isometries up to some normalization factor. And when you fix them, you can do the integral of x, and it becomes that x dependent, or here c is the 1 over chordal distance. So this 2-point function, because of isometries, is just a function of difference of this point. So you will end up with 2-point function of free field theory times this normalization factor is squared. And so unitarity of bulk will give that this rho should be positive. And then using some analytic continuation from de Sitter, because all of these correlators can be defined from analytic continuation from sphere. And in particular, the correlations are in Bunch-Davis vacuum defined from de Sitter. And then with some sort of Frost-Gripov type inversion formula, we found that, and this is the form of that formula. You just use the analytic continuation from the sphere and find it. You can find a similar equation that from orthogonality of harmonic function inspired by ADS calculations that has similar, they're equivalent, but the integral is from minus infinity to minus 1, which is over the discontinuity of this 2f1. And this is the rho, and we found some solutions, examples. So first of all, we check the formula by free massive field theory that it should give the delta function, and also some other correlators like phi squared in free massive, and also a CFT in bulk. One thing I forgot to mention is that this integral of delta for this particular for scalar field only the integral of this is only on principal series. There are some contribution for particular external dimensions phi that are type of pole crossing that can interpret as complementary series, but here the complete set of states with principal series. And this inversion formula actually, by being a convergence, proving that. And also, one can deform this integral over this principal series, which is from the constant d over 2, or from minus I infinity to plus I infinity, deform it, and pick up the poles. And the position of poles is giving us where the external dimensions are, which can be generated in some random complex operator, and also the bulk to boundary coefficient in this expansion that I showed you. So let me go to the main part that I start with. So we have a 4-point function of the now boundary operators, and we can do the similar thing we did for this 2-point function, injecting resolution of identity between them. And then again, you will have this type, like 3-point function type thing, which is O1, O2 external dimension, and this states delta and X, which look like a conformal a primary operator in conformal theory. And then these 3-point function are fixed by conformal symmetry again, up to some factor, and similar. You have some kind of F squared here, which is for I, and it has positivity condition. For example, if you take your 4-point function to be O dagger, O, it's just positive. Just few implication of this before the main part, which is Bootstrap, that for this O dagger, O for generalized fifth theory, you will see there's a necessity of ultra local terms, which are part of the delta functions, very local, and you have to have that to maintain unitarity. Also, we found some bounds for breakdown of perturbation, perturbative unitarity for lambda phi 4 with some perturbative calculation. But the main point is that we can have a crossing equation plus this positivity condition, and this is basically a Bootstrap question. And to start, as a matter of principle, we just start to look at d equal to 1 and all real operators, identical operators of 4-point function of O. And since the integral I showed essentially could be divergent, we regularize this integral by introducing some functional over cross ratios that, after doing this integral over cross ratio, it spits out two parameters, lambda, gamma, and sigma. And you reach the crossing equation that looks like that. Here we have additional sum, which is, because it's d equal to 1, as I told you, we have in addition to principal series, discrete series too. And this d here is from disconnected part. So by assuming some gaps, like the support of this integral over principal series, one can obtain some bounds. So we assume some that I knew is 0 to up to some point. We can just plug in and see some bounds. It's just a number over. So since it's essentially a summary talk, I just conclude with Fisher direction. So one question is that what type of irreps will happen? So I said, oh, okay, this principal series is there up to some pole crossing? But in general, there is a general question that if you have a spinning operators, also like more than 2-point function or 4-point function, what's going to happen? So one way to study that is like you take free field theory and you decompose the Fock space into representation and you see what's going to happen. Or similarly, you can take CFD and decompose conformal multiple SOD plus 1, 2, or bulk CFD to SOD plus 1, 1 to see what's going to happen to this representation. Also, one can study Kallen-Lehmann now for spinning operators. And also, we assume some gap and did the study just as matter of principle that it gives non-trivial bounds. But it's important that we have some phenomenological input to understand where to look for this Bootstrap question. And also, we came up with this regularized crossing equation, but it's better to have a systematic way to approach that Bootstrap equations. And one can actually use the orthogonality of partial wave, conformal partial wave, to change the crossing equation to integral over this partial waves on the both sides and remove the position dependence and have an integral over a T-channel partial wave coefficient and S-channel with an integral over, these are six H symbols. And that's also an equation we find, but it's important that focus on it and see what we can get out of it. And last thing is that how about gravity? If we want to add gravity to this scenario, how do we first set it up and what we can look for? And that's it. Thank you. If I don't ask questions.
Maybe you already answered this question. But if you take the fusion of two operators, the dimension of the double, like if the operators are heavy,
Yes.
won't the dimension of the double look like plus just b over 2 plus
Exactly. So that's what the part I said. So in the beginning, so this delta k, which are the dimension of operators, are different from this representation. And you can see here in this plot I'm showing here, they actually move on the right side.
And I mean, if you were magnetically away from this useful other numbers, like it's not exactly.
So that there is this, since there is no state operator correspondence, we have these states that are there always in principal series and they're there. But when you have the operator and they are not free field theory, the operators are essentially some complex. And if you, for example, perturb it with lambda phi 4, they're going to move to the right, to the operators of your theory, the boundary operators. So yeah, so essentially they can be.
But they remain discrete side.
Yes, the operators, yeah.
Okay.
You mentioned about some Bootstrap contribution, but the total function at the breakpoint.
Yes.
Could you expand a bit?
So yeah, that was like that was actually a puzzle first, because we didn't. Usually, when you're doing calculations, CFD, you get rid of these local terms, right? You don't care about them. So we did the calculation just for general theory to find these i's and check if it's positive, right? And for some particular spins, but it was not positive. It was a big mystery. And if one is careful and take a bulk two-point function in the bulk and take them to late time in the Caesar, we can see that it will recover the CFD 2-point functions. When you have a 5, it's going to be O plus O dagger. It will produce as O CFD 2-point function, O dagger CFD 2-point function. But there is a redundant part, which is O dagger 2-point function, mean field theory, and that's not 0. And when you take that into account for free field, it gives the right positive partial wave coefficients, which is like unitarity is telling you that you have to take them into account, which is some non-trivial observation here.
Any other question? I don't see the chat with any question. Okay, so if not, let's thank